use a little bit of a different scenario here, so I'm going to be using a little bit of this camera here, a little bit of the slides, and a little bit of Desmos. So hopefully you can track all those, and I will try to make sure to include a refreshed link to the slides for this unit in the email when I send you this documentation. So our goal today is going to be to look at Euler's form, which is this e to the I theta equals cosine theta plus I sine theta. Like, where does it come from? Why does it make sense? So we're just going to go through where those ideas are coming from. So here's the definition, right? Where is this coming from? So what we're going to be doing is we're going to be looking at Desmos and these things called Taylor series. And so I'll show you here. So a Taylor series is a thing they do in calculus, which we're not going to get too deep into, but we're basically things that are complex, these complex functions like sine or cosine or e to the x. They can be really, some of them can be difficult to work certain types of calculus procedures and functions and ideas on. So instead they sort of approximate them using these functions. So we're going to look at them really quick. So when you look at them, right, this is the graph right here for x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. And you can see when you look at it, oh, that looks pretty much like sine, right? Like, and so you could extend this function out indefinitely, right? So if you were to do this forever, it would be approximately the same as sine, right? When you look at the other one, right, 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, so on and so forth. When you look at how that graphs, that one approximates cosine. And then the last one down here, it's a little bit harder to see, but this is very similar to e to the x. You can't see it super well here, but see, as you zoom out, you can see it begins to approximate it as x goes to infinity. So it doesn't work as well as the others, but you can see as you move this way, it's approximating that same curve. So what we're going to do is we're going to be looking at this activity, which I'm going to also include in the email for you. But what we just said is that we have 1, 2, 3 graphs that we looked at, and each one of those graphs is approximately equal to one of those 3 functions. So this one right here, this one is the same as sine. Whoop, let me pull it down for you. As sine. And this one right here is approximately the same as cosine. And this one is the same or approximately the same as x goes to infinity as e to the x, as those 3 functions, okay? So that's what those 3 are equal to. So where this e to the I theta thing comes in is we're going to, and I'm going to cover a little bit of my work here so you can't spoil the punchline of each of these things here. So you might need to pause as we go. But what I said is that if I take this Taylor series, e to the x, which is right here, if I replace every single x with I theta, so instead of being e to the x, it's e to the I theta, you would get 1 plus, that becomes I theta, plus x squared becomes I theta squared. That one becomes I theta cubed, right? So on and so on and so forth, all the way down the line, okay? Which doesn't seem very impressive at this moment. But what we're going to do next is we're going to simplify it here, okay? So in order to simplify this, you need to remember a couple of different things. First thing you need to remember, which is important, is that when you have I to the 0, I to the first, I to the third, sorry, I to the second, I to the third, I to the fourth, as you continually raise I to a power, you're going to get like this rotation thing here. So you're going to always get one of 4 answers. 1, I, negative 1, or I to the third, which is negative I. This simplifies down. We're going to simplify this down to negative I. Okay? So let's look at them independently. 1, just 1. I, just I. But I squared becomes negative 1 theta squared, right? So that simplifies down to that. I to the third, we just looked at that. That's negative I. So I to the I times theta to the third is going to be the same as negative I theta to the third, right? And these denominators are going to stay the same across because we're not going to be messing with them. I to the fourth, that's 1. I to the fifth, that's just the same as I. I to the sixth, that's over here, that's negative 1. I to the seventh, that's negative I. And then I to the eighth, that's back, here we are again, back at 1, okay? So now what we're going to do here, and I've underlined them in different colors, is we're going to break these up into, terms with i's and terms with no i's. So we have the real terms, there they are, and we have the imaginary terms, boom, boom, boom. So we're going to rewrite them. Pause if necessary at any point along the time to track what we're doing here, okay? We're going to break them up. So now we have all the reals over here, and remember, always consistently saying this is the same as e to the I theta, right? This is what we've been doing the whole time. Pull all of those real terms into one grouping. Pull all of the imaginary terms into another grouping. Now, it's at this point when you might start saying like, hey, I think these are rather similar to these expressions here, right? These look a lot like these. So what we're going to say is this set right here, well, that's just cosine, but instead of x, it's cosine of theta. So that part becomes cosine of theta, okay? That one's really easy. So that would be all of the lines, the ones that are in black, okay? And then the next thing you need to see here, which is a little bit tricky to see at first, but if you factor this I out, if you undistribute it basically from all these terms, you can say I times these terms, and of course this pattern goes on indefinitely, but just for today, I times, well, there it is. There is the other term, the other set. This is sine. So this becomes all those blue terms, right? That's all of these. So what you get when you replace, so the big picture here, let me zoom out a little. The big picture here is that when you replace e to the I theta, right? If you take e to the x and you make it e to the I theta, you break it out, you simplify it, you can see that this pattern is the same as this. This pattern is the same as this. And of course, right, this would go on indefinitely, oscillating between real and imaginary terms, right? So this is not just, hey, it isn't just these 4 terms, right? This is indefinite. This is happening out to the infinitesimal, okay? So this is where this idea comes from, which is sort of the beauty of the whole thing. This is what mathematicians tend to call one of the more beautiful mathematical functions because it ties together so many different ideas. So next, occasionally you see this tattoo. It's like if you want to really know a nerd's worth, if they've got this tattoo, you know they're nailing it. So what this says e to the I pi. So we're going to look at just this part right here. We're going to think of it over here. E to the I pi. Well, that's the same as cosine of pi plus I sine of pi, right? And this is our cis term, right? This is our cis theta. This is what we were going over last time, where for this instance, r is just 1 because it's not really noted anywhere. So, right? So this would be 1 cis pi if you wanted to condense this expression down into the condensed form. And theta would be pi. So if we wanted to plot this, on our circle again, we would say pi, that's over here, okay? And 1 out from the origin, right? That would be over here at -1, okay? So what they're saying is this is -1 plus 0i, or in other words, just -1. So all of this part right here, this is all just equal to -1. And this part, plus 1, that's just saying if you take this expression here, which is the same as -1, plus 1 equals 0. Oh yeah, okay, so -1 plus 1 equals 0. But the reason this is considered like one of the more beautiful equations in math is because look at all of the things it includes. We have e, one of the most famous irrational numbers. We have pi, one of the most famous irrational numbers. We have I, the imaginary number. We have the additive identity happening here and the multiplicative, right? So we have 1, we have -1, it's opposite, and we have 0, right? So it's tying together all of these different ideas in a single expression or a single equation, which is why mathematicians think it's so cool. Okay, so review. Let's sync all this up because it's been a while. So if I want to write something in these 3 different forms, either of the 3 forms of complex numbers that we've learned. Okay. If I want to write something in rectangular form, I need to have its horizontal location and its vertical location. So it's more about how far over, how far up, where does it live? Okay, that's how we write rectangular. This is sometimes called Cartesian. You might see it labeled Cartesian. Polar/cis. Unfortunately, your calculator is going to oscillate between polar as Euler's form, and sometimes you see IB writing polar as this cis, but be flexible, look for those context clues to see exactly what you're looking for. So in order to write something in this rcis theta form, what you need is r, which is the modulus, ooh, fancy word, which is the length, remember? It's the length of it, so from here to here, right? From here to here, anywhere on the circle, how long is it? And theta, which is your argument, that's another fancy, there's no e there, argument, which is the rotation. How far did it take rotationally from here, right, always from the x-axis, starting point, to get there? Positive direction, negative direction. And then what's cool is that actually, because these 2 ideas are so similar, shifting back and forth between these 2 things, it's just rewriting it in a different way, right? So that means that all of the things we said here, same as above. So we'll just do a couple really simple ones. So if I had 5 cis theta, let's make theta, let's just make it 0. That would be the same as e to the 5, just kidding, e to the 0 times I with 5 out front. Okay. R being the magnitude, e to the I, and then the angle of rotation. So if I had 7 cis pi over 2, I would just write 7 e to the I pi over 2. And both of these 2 things you would draw the exact same way. You wouldn't use your horizontal and your vertical location. You would think, okay, pi over 2, that's a quarter turn this way, and then 7 or 5 up, right? I just come up there and be like, that's how long it is. Okay. So these 2 are really interchangeable. Let's say you wanted to go the other way. 12 e to the I negative pi over 3. Well, 12 cis negative pi over 3. You don't need the I. It's implied in the transition. Okay. So what I would suggest, my dears, is just practice doing a few of these going into cis form. It's real easy. And also practice going from this form into e r e to the I theta. And the best part is, whisper, whisper, is your calculator will do it for you. If it doesn't do it for you, or if IB is asking for you to do it by hand, remember, draw where it lives, 1 over root 3 up, right? So 1, this is 1 long, this is root 3 long. And then just think of it, 1 long, root 3. Think of it as a triangle. Okay, there's R. There's just some simple right triangle trig to figure out what theta is. Okay. Only do it by hand if you can't use your calculator, right? So if it was like A plus BI, in that case, you would have to sort of create like a general rule using algebra. Otherwise, you're going to plug it in your calculator. I'll just show you. Come on, wakey, eggs and bakey. Let's just do 3 plus 2 I, enter, and look, see, it already did it for it. It wants to automatically put it in this Euler form for us, okay? Menu, where did they go? Number, sorry, complex number tools, and then let's just say, take it back to rectangular. Boom, there it is. So it took the thing that we gave us, where we gave it, we turned it into Eulers. There's our Euler, put it back into rectangular, check, check, check. Very straightforward, okay? The only ones that are particularly challenging are when they ask you to start with just like variables, and you have to actually run the algebra, but we can look at a couple of those when we get back to class. So hopefully this helps you make some progress on your packet, and I will see you soon.